Well, in any event, as we go through this, I'm sure there's some questions that'll pop up. I'm happy to answer the questions. We'll go through them. We got 3 hours to do an hour's worth of work. It should be adequate. If it isn't, we'll punt. But I'm going to, you see that funny looking guy on the screen? Can you guys, is the monitor working well enough to get you done? What's that?
Introduction.
We'll do the self-introductions. We'll start with Rick.
Rick, KM6MZY.
Alan, KO6AGW, new general.
Congratulations.
I'm Bill, November 6 Hotel Alpha.
I'm Noemi, N3ARB.
I'm Cam, KB3LMR.
James, AE6JG.
Mike, KO6CIL.
John, KO6 Cal.
Kishore, KR6RAO.
I'm Wilson, N6EMF.
Gary, KG6SMX.
And Gert, KK6ZGA.
And believe it or not, I'm Phil, KD6RM. And believe it or not, I'm actually the club president, if you can imagine such a thing. So in any event, this funny looking guy up here, has anybody heard the name Bob Pease? Does that mean anything to anyone? No?
No, but that character looks...
Looks like Benny Hill.
You know, he
Vaguely.
he's an MIT grad. He's now deceased.
Is he?
He was the chief scientist for National Semiconductor, and for years he published a column called Pease Porridge. And every time he'd have a column, it'd start off with, "What's all this blah 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 stuff about anyway?" I thought that was a great way to start this, because what I've got going on here is the first question. Is that thing going to click? Oh, that is my problem. How about this one? Oh, there we go. So, what does 10 meter or 2 meter band mean? Gentlemen, names. Names.
Steve.
Steve.
Bob.
Bob. Steve. Is that Bob Launderville?
Yes, I do.
So in any event, we got another name.
Ben.
Ben.
Yep.
Oh. Yeah, Ben Parrish. So there's a lot of chairs over there. We're probably going to have to drag some out. I apologize for the size of this room, but meeting space has been a bit of a challenge for us lately, and it shows. So in any event, anybody have an answer? What does 10 meter band or 2 meter band really mean?
Well, it's the frequencies that we perceive as having a 2 meter amplitude or a 10 meter amplitude.
It's wavelength.
But it's wavelength. Because
It's wavelength.
Yeah.
You know,
Do they correspond?
I'm going to show you. In the world of electromagnetic radiation, which by the way covers anything from down in the infrared range all the way up to light, long past microwave into what's called angstroms. Do you know what an angstrom is? It's 1/10,000,000th of a meter. And in every one of those instances, when they talk about wavelength, it's actually how long that actual wave is. So in the 10 meter band, guess what? The wave is about 10 meters long. A meter's a little over 3 feet, right? So 10 meters, that's about 30 feet long wave. And the way you determine that is what I show up here. Wavelength is velocity. Do you know what the velocity is of electromagnetic radiation?
Speed of light.
Speed of light, nominally.
Which is 300 million meters per second. If you use meters, it's a lot easier to figure out this wavelength thing, right? So in any event, if you take 30 million cycles per second and divide it into 300 million meters per second, it tells you that each one of these waves is 10 meters long, right? Pretty cool.
It works.
And the same thing's true with 2 meters. And there's this cute little diagram. There's a crest and a trough and a crest. And if you do light, those meters get really small, right? The wavelength gets really small. So now you know what 10 meters is all about, 2 meters is all about, 17 meters is all about. It's just the length of the wave. Am I going to melt in here?
Melt?
I think so.
I'll see if I can get them to go turn down, because it's getting warm in here.
It's getting plenty warm.
Phil,
Oops, wrong.
is the length measured peak to peak in that diagram?
You can move it back and forth. You can use the sine wave crossing. You can use trough to trough, crest to crest. It's all the same thing. It's how long the actual wave is. So, and there's our bands. And lo and behold, if we look at 10 meters, wherever the hell that thing is, it says we go from 28 megahertz to not quite 30 megahertz, and I use 30 megahertz as an example, right? So now you know why people call them 10 meter band, 17 meter band. It's how long the wave is. Pretty cool, huh?
Excuse me, Phil,
Yes.
could you move that thing down more towards the center of the
Which thing?
table, your screen, your computer screen?
You want to look at it?
Yeah. Now I'm sort of seeing more of you on this
Do you
side.
think you'd reach on this white table, Phil?
Could I which?
That's a lot better.
Could it go down on this other table potentially, or is that, will not reach?
Oh, it'll reach. I just thought it'd be easier if it was a little higher.
It's fine.
You know, you're talking 2 feet difference. I don't think that's going to make much difference. It's a little higher. I think that might.
A wavelength, but it's a lot better.
I think
Tell these guys, tell Wilson to shine his head so you can look through it.
Phil, I think if you move that chair, you could shove it over so it's centered on this table. I think that's what they're looking for. If that would be.
If I don't destroy something in the process. How about that? Does that make it better?
Hey, way to go.
We aim to please.
Thank you.
You're hired.
All right, so here's your bands. The HF bands, right? And it actually includes the VHF and the UHF bands as well. She knows how to do all this stuff. You thought we were going to freeze. Oh, you're good. You know, this is a room full of highly technical people.
Who can't manage a thermostat.
They didn't even know where it was. So let's start talking about antennas.
There you go.
Thanks again.
You're welcome.
There are 2 types of antennas. There are resonant antennas, and there are non-resonant antennas. Anybody have an example of a non-resonant antenna? Come on.
Service station down near Mather where the FAA controls all the aircraft.
Run that by me again.
The air route traffic control center is just this side of Mather Air Force Base. There's a lot of antennas there.
Non-resonant?
Well, nobody lives there. A lot of people live there.
Boy, I should never have started that.
Are we talking about long wires and things like that?
A long wire is an example of a non-resonant antenna. If you want to cheat, you can look right up there. I gave you the answer. Most of what you're going to work with are resonant types of antennas. The most common one is the
Dipole.
Exactly. And in this day and age, we've changed that ever so slightly. We've got this new thing called end-fed half wave. And guess what? It's the same antenna. Identical, same antenna performance-wise. There's just a difference in how we feed it. Okay? So we're only going to deal with the resonant types tonight because that's what you're going to run into unless for some reason you've got a long wire and an antenna tuner or things of that sort. But the most common antenna type is the dipole, and in this day and age that's a toss-up with the end-fed half wave. Everybody's familiar with those, I trust? Okay, let's move on. Resonance. Would somebody like to define resonance for me? Let me ask you this question. If you put too many clothes in the washing machine and you spin it up real good, what happens?
It thumps.
Why does it thump? Why does it vibrate?
Out of balance.
And yes, that's true, but why does it vibrate?
It's the resonance frequency.
It's the resonant frequency of the washing machine itself. The same thing happens in your car if you got a wheel that's out of balance. Have you ever noticed that when you have a wheel out of balance, there's only one speed at which it goes hopping down the road? Guess what? That's the resonant frequency of the automobile, the entire assembly. There was this guy, Nikola Tesla. You're familiar with that name?
Yeah.
Several years ago in New York City, he decided he'd determine the resonant frequency of the building he was in. So he hooked an apparatus to the building and he started pulsing the building. He had the whole building shaking because he discovered exactly what the resonant frequency is. So resonance is a property that exists everywhere. The tuning fork, you're familiar with the tuning fork? You hit one of them and it's resonating. Why is it that frequency? Because it's its natural resonant point. And you can actually take a second tuning fork, put it next to the one that's vibrating if they're on the same frequency. Pretty soon, the second one steals a bunch of energy from the first one, and they're both singing at exactly the same frequency. That's an interesting concept, isn't it? And an awful lot of what we work with is based on that concept. So what I've listed here is the resonant frequency of an antenna is determined by the electrical length of the element. But more important than that, resonance is defined as the frequency where a system absorbs the most energy. So that works for a washing machine, it works for your automobile, it works for your antenna. Resonant. I'm getting a look like, what am I talking about? Does that make sense?
It does.
That's how it works. That's exactly basic physics stuff. That's how it works. I want you to note this child in the swing. And you may not be aware of this. Are you guys familiar with a pendulum?
Yep.
Tick tock, tick tock, tick tock.
Yep.
What makes the pendulum an accurate time base?
It has a resonant frequency based on the length of its...
The length of the arm. The length of the arm. So a child in a swing, no matter how hard you pump in that swing, you're going to swing back and forth at exactly the same frequency. You may only go that far or you may go that far, but the periodic motion is exactly the same because of where the center of the mass is compared to the pivot point. So if she stands up on that swing, she's going to swing at a faster rate because the length of the arm is shorter. And if you were to lengthen the chain, she'd swing slower. Resonance. We got the same thing with antennas, believe it or not. A long antenna is going to be at a lower frequency resonance than a short antenna. Did you know that? Say yes.
Yeah.
Yes.
Star students, I'm liking this. So here we go. Two basic resonant antenna types. I already gave you the answer for the first one. The dipole, right? And what used to be the second most popular was the inverted V. Times have changed. People don't have towers anymore. Make sense? What's the advantage of the inverted V over the dipole?
Height.
Not necessarily.
No resistance.
Not necessarily, no.
Little less space.
Shorter space.
One support versus two. That's why people put up inverted Vs. Pretty exciting stuff, huh? It's not everybody I share this with. Other resonant types. James knows about the first one. End-fed half wave.
Is that the one I built?
I have no idea. I stole that off the internet.
It's not the line.
Then there's this other thing called the oft center fed dipole, which is also a resonant antenna, but we cheat like the dickens. And in antennas, there's an awful lot of cheating. If you want to be good at antennas, learn how to cheat. You think I'm kidding?
Is that why you're good?
I'm not good. My wife's always telling me I'm bad. So here's another type of antenna that is actually kind of HOA friendly. Does anybody here have an issue with HOAs? Raise your hand. That's it?
Hey, Tony, here, I'm gonna share for you.
Come in, come in.
You know, traffic's there's enough space to share.
No, that's fine, yeah.
We're doing pretty good attendance-wise. So anyway, the beauty of the vertical option is there's not much of a footprint, and oftentimes your neighbor doesn't notice. Now that's the beauty of HOA restrictions. It's only an issue if they can see it, and if they're willing to do something about it. So as I said earlier, with antennas, learn how to cheat. How's that?
Works for me.
Worked pretty good, doesn't it? I've got several examples of how I cheat. So here's some other antenna options. These are multi-band options. Everybody's heard of the G5RV, which by the way is not really a resonant antenna. See out at the bottom it says, see, you got to go to the tuner, However, the beam, as you see, is a resonant type of antenna. So far, so good?
That is a beam antenna?
On the right,
Okay.
with the blue sky.
Yeah.
We don't have any blue sky on the G5RV.
Yeah.
We sell blue sky.
I'm sure you can get some out here.
So here's, by the way, both of these are resonant antenna types.
It's going to be a second.
Oh, it's going to be a second. I screwed up. I put my hand in my pocket.
Turned it off.
Probably the keys.
Yep.
So in any event, the magnetic loop is a resonant type of antenna, and the buddy pole is also a resonant type of antenna. These are little portable antenna designs, and they're both fairly effective. They're not as good as their full-size counterpart, but you'll see a lot of this stuff. Now, I think I did mention to you, I know very little about any commercial product. Practically everything I do is something I make. So if you have a question about Comet's this or some other manufacturer's antenna, I probably do not have an answer. How's that for getting out of it?
Wilson does.
Wilson's got answers? I like it. So in any event, let's talk about the one that most ham radio guys are absolutely obsessed with, SWR. Would somebody care to tell me what SWR is all about? Come on, come on.
Standing wave ratio.
Very good.
I know that.
What's that mean?
It's the ratio between the power extruded and returned.
Right. It's a relationship between how much power goes down the line and how much power comes back up the line. And I'm going to give you an example about this that will just blow your mind. Is anybody here familiar with the old days of television, you know, when the transmitter was up on the mountaintop and every now and then everything was great and then all of a sudden you get a whole bunch of ghosts? Has anybody ever seen that?
Oh, yeah.
You know what caused that?
Reflection?
Yes, it does. What happened, and we had a TV station in my Hicktown home of Reading, in the wintertime, their antennas would get iced over. And you can imagine how well your antenna matches when it's covered in ice, right? And so they got these TV transmitters on top of this mountain, probably 50 kW or 100 kW, I don't know how much power they were. But pretty soon, you get too much ice on it, and you're watching TV, and you got the image, and then you got a ghost of the image, and another ghost of the image, and another ghost of the image. You know why?
Varying the frequency, we're getting
the reflections were eventually reflected back and actually transmitted on the delay?
What happens, you send power up the antenna, up the feed line to the antenna, it's not a good match. So a portion of that power goes back down to the transmitter. You think that's the end of it? No. Because then the transmitter takes that same piece of energy and it sends it back up to the antenna. And some of that energy gets radiated. Oh, and by the way, more of it goes back down the transmission line of the transmitter, and then it bounces back, and so you'll get 3 and 4 and 5 images, all from one transmission. And it's all due to this reflected power. That is the most descriptive definition of SWR that I can give you. You can actually visualize what's happening. Here, bounces, bounce, 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 until all that energy finally dissipates, and then you get to the next transmission, and it just keeps going. So, SWR is a measure of power delivered to the antenna compared to power reflected back from the antenna. That's all there is to it. It doesn't mean that the antenna is not resonant, does it? It can, but not necessarily. The only real significance of SWR is the protection of your transmitter. You know why?
You don't want to fry it.
You won't blow your fines.
That reflected power can heat it up and then burn it up.
In the old days, when we had vacuum tubes, you'd load that baby up until you had these variable capacitors arcing away and say, that's just about right. In today's world, when that happens, the output device in your transmitter is what?
Transistor.
Transistor. Are transistors voltage sensitive? You bet they are.
They don't want heat too much either.
Yes, and by the way, just so that you know, 2-to-1 SWR is kind of the standard we all shoot for. You want your SWR under 2-to-1. That amounts to, if 10% of the energy reflects back from the antenna, that's a 2-to-1 SWR. Only 10% of the energy gets reflected back. And that's where it gets pretty delicate, because most rigs barely live with a 2-to-1 SWR. Only 10% of the energy reflected back. That's kind of interesting to know, isn't it? Efficiency of your antenna is not affected by SWR. Antenna works just fine. Transmitter's not happy, but the antenna's fine. By the way, typically it's cheaper to replace the antenna than it is the transmitter, but it's money. There are issues regarding power loss in the transmission line due to SWR. So as I said, you got this energy going up the transmission line and gets reflected back down, less the energy that was dissipated by the antenna, less the energy lost in the transmission line getting to the antenna, less the energy lost in the transmission line coming back down from the antenna, right? Those are the losses, and the higher the SWR, the greater those losses are. So there are some issues with that, but in most instances, the guy on the other end has no idea that there's any difference. Yes?
Question, so when you say efficiency is not affected, is that the gain of the antenna?
Yes.
Of the power emitted?
The antenna is working just as it should. So we're going to get into this a little further. If the load antenna connected to the transmission line has the same exact impedance as the transmission line, there is a perfect match. SWR 1-to-1. By the way, that occurs at only one frequency. So for example, in your transmission on 40 meters, and you've got your antenna set up so it's a perfect match at 7.15 megahertz. At 7.16, it's not a perfect match, is it? Probably pretty damn close, but it's not perfect.
Okay.
So you see, the property of resonance and the properties of impedance all fall into play. And I'm throwing these words out to you because they're the ones you're going to need. And by the way, those words are in that book, should you choose to refer to it. And we're covering this, as I said, in 24 slides. Doing all right there, James?
I'm impressed.
Oh, good.
I particularly
I'm depressed.
I remember watching the Watergate hearings and TV kept ghosting, and now I know why.
There you go. Let's talk about impedance. This is the biggie. A dipole has an intrinsic impedance of 72 ohms, height dependent. What's that mean? Height dependent.
Height above ground?
Very good. Which ground?
Surface of the earth?
No.
Not necessarily.
Vertical ground?
You know, sometimes real ground is 2 feet below where you're looking. Sometimes it's 10 feet below where you're looking. It all depends upon the reflection characteristics of the ground. So you have no real answer. It's dependent upon the characteristics of the earth.
We talking about moisture level and things like that?
That's part of it.
And mineral content?
Mineral content's part of it.
Okay.
Whether or not you had a glass of whiskey is part of it. Woo! Okay, so an inverted V has an impedance, characteristic impedance, of somewhere between 40 and 65 ohms, dependent upon height and angle. You know, you got this V thing. If you move it out this way, it raises the impedance. Yes, and if you move it in this way, it lowers the impedance. So sometimes you can get a really good match on an inverted V by how you have these two down leads positioned. Pretty clever, huh?
Is impedance good or bad? Is more
Impedance is just a property. You know, it's whether you're 5'6" or 6'5". It's just a number.
You can still walk.
As long as your feet still hit the ground. That's the deal. Okay, so commercial vertical antennas with a good radial system have a characteristic impedance of 36 ohms.
36.
Half of what a dipole is, 36 ohms. Rarely will you find a vertical antenna. I'm talking about a non-trapped, non-custom manufactured vertical antenna. So you got the vertical element, you got the radials, they're tied together at the base, you measure the impedance. Typically you're going to have an impedance higher than 36 ohms due to losses. Ground resistance losses and characteristic impedance losses. Okay? Commercial antennas are designed for 50 ohms. When you get one home and stick it on a mast, it's not going to be exactly 50 ohms. Why?
It's still going to be affected by its distance from ground, etc., that sort of thing.
Amen. Exactly right. Exactly right. Here's a real interesting one, and we've done clinics on this. There are a variety of impedance matching techniques. We did a NanoVNA clinic a few months back. It ran 2 sessions, and we did 2 groups of 2 sessions. And we taught people how to calculate and design antenna matching, and it was duck soup. Anybody ever had duck soup?
Nope, just duck.
Just duck. Duck soup's cool stuff. So there's a variety of impedance matching techniques. An antenna tuner is an impedance matching device. So far so good? Makes sense? Everything's logical? Impedance has 2 components. There's a resistance component and a reactance component. Would anybody like to tell me what the resistant component is? This is the test part. They're not buying any of this, are they?
I don't think so.
Yeah.
It's
The way you should look at this, say you have a 100-watt transmitter, and you hook it to this, nothing more than this piece of wire that's cut in the middle with a piece of coax coming out of it. And if you make a measurement, a 100-watt transmitter, well, we're going to do some high-level math here. Power is equal to current squared times the impedance, the resistive components of the impedance. So if it's a 50 ohm antenna and you're dissipating 100 watts, that means that 100 watts it's the square root of 2. So the square root of 2, it's because it's the current squared. So 2 times 50 is 100, right? Here's your 100 watts. So the amount of current going in that antenna is the square root of 2, which is 1.414 amps, right?
Okay.
Well, where did it go? What ate up all that energy?
Two things.
Oh, Wilson, tell me.
One is a little bit of heat based on the resistive loss.
Now, we're going to forget those.
And then the radiation.
The radiation resistance.
Radiation.
The radiation resistance. What's that saying is that piece of wire managed to take that energy and convert it into these big electromagnetic waves that you're using to talk to your buddy down on the other side of the world. Radiation resistance. And that's that R number. R is the radiation resistance. And that's the one that does the work. Does that make sense?
Okay.
Simple math. P is equal to I squared R. Ohm's law. Now, by the way, I forgot to mention this at the start. Amateur radio is a social activity based upon a technical hobby. And it's absolute fact. If you stop and think about what it took you to get a license, what did they test you on? Communication skills with your voice? How well you type? Color your hair? It's your knowledge of technical phenomena. Physical, technical phenomena. So the hobby is based on technical skills. But most of us think in terms of how much fun it is to talk to Pete, right?
Or
So
unbox
it's
the radio, Phil. Unbox the radio.
Yeah.
Don't even start.
Pull that plastic off.
Yeah.
Phil
I can
doesn't
still
buy
hear my
radios to
brother-in-law.
unbox.
If you did.
You should put it in a box. Then
Actually, I do have a boxed radio.
Oh, you do?
And it's a fine one, I might add. So the bottom line here is this antenna impedance thing is the one thing that will drive you crazy about antennas, and it's the one you really want to know about. Okay? Does that make sense? It's in that book, by the way. You want to thumb through it? And
Maybe Gert can read a chapter.
Gert would be happy to do that.
So Phil, if I have my, that's a good point, if I have my antenna tuner plugged into my dipole, and I'm trying to get a SWR 1-to-1, I start trimming the ends of it, eventually I'll get that 50 ohm match.
If you have an antenna tuner, you don't need to trim the ends of it.
Well, antenna analyzer, sorry.
Analyzer.
So I'm analyzing my antenna.
Boy, are you in trouble.
And I'm trimming the ends to get 50, but it's supposed to be 70 something, right? So,
You're wrong.
right. Maybe you're wrong.
Remember when we did the NanoVNA?
I wasn't in that class.
Oh, you didn't get in that class? The problem is, and we're going to get to this in just a second, that piece of coax, it'll lie to you. The SWR that you read's right. It's exactly right, or very close to right, because there's some losses, that are coming down the feed line. But when you try and read the R values and the X values, we're getting into that now, through a piece of coax, those numbers are wrong. Because a transmission line is an impedance transformer. I remember an example. I was living over in Napa. I put up a little dipole antenna in my attic because HOA restrictions. I got it where I thought it should be. I went down, put on my antenna analyzer, and it was way off. I thought, well, hell, I know how to figure this out. I did some quick calculations, went up in the attic, cut 17 feet off each end of that antenna. It was off even more. Oh, how can that be? I went through everything right, I measured it, I calculated it, I cut it, and it got worse. And it continued to get worse. And I'll tell you the reason why here in a few minutes. You cannot sit in your shack, put an antenna analyzer on your antenna, and measure these two components, the reactive and the resistive components, and get the right answer, unless that piece of coax is exactly 1/2 a wavelength long. That's the only time you'll get the accurate answer.
Oh.
I'm seeing looks on faces here that are frightening.
Yeah.
But it's absolute fact.
That's an interesting phenomena.
Phenomena.
Yeah. So does,
That's sort of like you go down to the store and you buy something and they charge you a small phenomena fee.
yeah. I'm just kind of curious whether like, is there any kind of like harmonic thing, like, 20 meters and 40 meters being double and all that sort of thing to those lengths?
As long as you get half wave.
Isn't it a multiple of a half wave? Or?
Yes, it is.
Okay.
Yeah.
Yes, it is.
Okay,
So let's look at this magic meter here. And I've had this thing forever. Mike Oretsky, who used to be the RigExpert distributor around here, he got so mad at me. This was an original meter. This thing's got to be 15 plus years old. And of course, he's always selling the new stuff. They're really good, really tricked out new stuff. And I was doing all sorts of exotic stuff using this little tiny meter, and it made him so damn mad because nobody's supposed to be able to do that. You got to have the new one to do the good stuff. And they all work quite well. So in any event, it's telling me right there, it says that the R value, the radiation resistance value, is 18.7 ohms. By the way, this is a vertical antenna. Remember what I told you the impedance of a vertical antenna should be?
36.
I got 18.7. Well, am I in trouble? Okay? And it also tells me that the X component, X is the reactance. So if you have a number, my reactance is a negative 183 ohms. So if you have a reactance of 0 ohms, the antenna is, right answer, resonant. If you have an answer that's a positive number, the antenna is too long. And if you have an answer that's negative, the antenna is too short. Pretty technical stuff, right? Long, short, just right. Just like the three bears.
Okay, so we need a Goldilocks.
We need Goldilocks.
Does that mean one positive is inductive and the negative?
Positive is inductive and negative's capacitive.
For those of you who are studying for your extra, I know this is a big feature of that study.
James did that.
Yeah.
There's a lot of extras around here. I know of at least 2 in this class. I don't know how many there are. How many extras? 4? 5? Why are you guys in this class?
We're good at taking tests.
Humility.
I never got an extra. All right, let's move on. So here's some interesting things. You see on the left, that's that little tiny NanoVNA, which I think is just the greatest little gadget that ever happened. You see how you got this big looping bottom thing, and at the bottom of it I got that arrow? You know what that indicates where that arrow is?
Was it?
That's the resonant frequency?
That's the resonant frequency. And in this case, that antenna is resonant, that F sub R, 7.16 megahertz. And the SWR, which is also measured, you see that green arrow? Oh, I got a little pointer, I should have grabbed it. You see that green, you see the half circle? And there's a little green arrow right in the middle of it?
Pretty much right in the middle of the chart.
Let me see if I can get fired up here. We'll use all this high-tech stuff. That's it's called a Smith chart.
Yeah.
I scare everybody when I start talking about Smith charts.
Actually, they're kind of cool once you figure them out.
You're supposed to do that?
Think they're cool?
I don't know, you're supposed to figure things out. Did I break this thing? Say yes. Oh, maybe not.
Any questions so far?
I'm solving the difficult parts of the world. Oh, maybe that's what it is right there. Let's try that. And then if I flick the switch to on, yeah.
There you go.
You're not going to see it on that screen. I was afraid of that. If we had a cat, we could make that cat bounce all over the place. But the bottom line is, on the Smith chart, this is zero reactance. And then this is inductive, this is capacitive, and right where the circle crosses that line is perfectly resistant, when the resistance is 0, or the reactance is 0, that's the resonant point. And so there's 2 examples here where we're looking at resonant. Oh, I can do it with this. Right there. Is that coming up? How come that's not showing up? Huh. Why wouldn't that cursor come up there? Well, in any event, where it dips, that's the resonant point. That's the resonant frequency. So on the left, the resonant point's at 7.16 megahertz. On the one on the right, it's 6.9. They're both supposed to be middle of the 40 meter band. So obviously, my frequency of resonance 6.9 means my antenna's a little too long, doesn't it? That's all there is to it. Too long, too short. Measured at the antenna.
Okay.
Measured at the antenna. Okay, so let's move on here. We're halfway through that book. Slide number 15. So I've brought along 3 different antenna analyzers. And we're in the business of giving money to manufacturers based on how well they convince us they have the right stuff, right?
Okay.
Truth in advertising. Maybe.
Marketing.
Maybe. You know what marketing means?
Got your attention.
Create demand.
Mm-hmm.
Create demand. So I'm going to pass these along. I think this is the best value on the planet. This is called an FA-VA5. It sells for about $200. 10 kilohertz. That's audio. All the way up through 600 megahertz. So you can do HF, VHF, UHF, low frequency, broadcast band. Your AM, FM transmitting station runs on 2 AA batteries, and it's got the ability to do very easily open short load calibration. We're going to talk about that. So pass that around. Then I'm going to pass along my good old RigExpert. RigExpert builds some great stuff, by the way. When my good buddy Mike Oretsky unfortunately passed away due to COVID, he was also the repair facility. So for a few months I became the RigExpert repair guy. And I'm going to tell you, I'm glad I got that job done with. It's all little tiny surface mount stuff, and I'm getting old.
Made you feel like you were going blind?
You think the FA-VA5 is a better value than this product family?
Oh, absolutely.
Okay.
For $200.
Right.
You cover everything from the bottom end all the way to the top.
Right.
And you can easily do an open short load calibration, which we'll talk about here in a few minutes.
So price-wise is where it's nice.
That's the value.
Necessarily better?
It's got every feature the other ones have.
Gotcha.
What is this value of this larger?
The RigExpert.
Oh, that one's old. I don't know.
Yeah.
The current RigExperts are like $450.
Yeah.
The AA230 is the popular one, but it only goes through 220. It doesn't do UHF.
I like using my my RigExpert better than my NanoVNA.
Oh, I'm sure you do.
It's just because it has a nicer screen.
It does. And it has a nicer price tag.
But the reality is that
But what I noted here is 2 recommendations for Antennalizer, most bang for your buck.
Sure. Yeah.
And this is the cutest little gadget on earth. Pass this along. This is that little tiny NanoVNA, $60. And it goes through 1,500 megahertz.
Different model, but
1,500 megahertz.
Yeah, it starts at 50 kilohertz and goes to 1,500 megahertz. I'm sorry?
Is well outside of our HF bands.
We got 1.2 gig. Part of our world. Yeah, it's unbelievable. And there's some other features in there that are just off the charts. I mean, it's a full-blown 2-port vector network analyzer. And I want to talk about that just briefly. In the days of my youth, which was a long time ago, if you were lucky, I was 11 when I was first licensed. No SWR meter. All you had was a tape measure, and you would adjust based on how much arcing you got and loading capacitor in your Pi network output. And the lucky guys had an SWR meter. This was 1959. None of this stuff existed. And somewhere in probably the 60s, the Hewlett-Packards of the world and the Tektronics of the world started producing vector network analyzers. They were $20,000, $50,000, $100,000. Full-blown laboratory instrumentation. For $60, look what you can get today. This is such a different hobby. It is so much easier. Every answer you need is in your hands for $60. I mean, it's crazy stuff. The bottom line is, you can do any damn thing you want for a song today. You just need to know a little bit about it, and that's what these 24 slides are about, a little more about it. Okay, so far so good?
Yes.
Now, let's talk about, what do I got next here? Oh, now we're going to talk about transmission lines. The beauty of that one is, it's much like the RigExpert in the familiarity of the screen and how the buttons work and all that stuff, but it's so much cheaper. Oh, and there's one other thing. The guy that produced this worked with another guy whose products I've been using for years. He has got software that works with that machine that does everything you can imagine. The software manual is 670 pages long.
And you want us to read it?
Absolutely.
After the antenna book.
No 24 slides for that.
No, I mean, the utility of that tool is just off the charts. I mean, the value.
NanoVNA, right?
No, I'm talking about that FAVA5.
Okay.
It's just an unbelievable product. The real practical thing about that is this open short load thing, which I'm going to be talking about here in just a minute. Remember I told you a transmission line is an impedance transformer? Remember I said that?
Yep.
If you look on the screen, it says transmission lines act as transformers. See, I didn't lie to you. And then it goes on to say quarter wave lines, if they're shorted, look like they're open. And if they're open, they look like they're shorted.
What's that all about?
The transmission action, the transforming action of a transmission line. And that's why I say you cannot believe anything you read when you have a piece of coax between you and the antenna unless you take the transmission line out of the measurement. And that's what you do with what's called an open short load calibration. It takes about 30 seconds, as long as your antenna analyzer supports that action. And so that old one that I use does not support that action. And then the NanoVNA does, as does the FAVA5. It's really easy to take the transmission line. What you do is you leave the coax connected to your analyzer, then you go out to where the antenna is, you put an open connection on it, you go back and say calibrate open, and then you put a load on it and you say calibrate load, and then you put one on that says short, says calibrate short. And what that does is it tells the antenna analyzer what it's looking at. It says, oh, this is a load situation, and this is a short situation, this is an open situation, and then it measures the true impedance of your antenna at the antenna down this long piece of coax. That feature is, if you're going to do anything with antennas and you want to know what's really going on, you need that feature. Otherwise, you're going to be up in the attic like me, cutting and splicing and cursing and swearing and wondering how you got to be so stupid. I'm actually pretty good at being stupid. So, transmission lines are always transformers, and you use quarter wavelength pieces of transmission line are very useful for a lot of things. For example, if you put up an open loop, a big loop, you know what the characteristic impedance of a loop antenna is? About 100 ohms. About 100 ohms. But if you take a piece of 75 ohm coax and you cut it exactly 1/4 of a wavelength long, and then take your 50 ohm coax and hook that to that 75 ohm coax, you have a perfect 50 ohm load. So that length, that quarter wavelength of 75 ohm coax transforms the 100 ohm impedance to 50 ohms. It's in that book. You want to read that to them?
Okay.
Okay. So there's a lot of things that you can do with this stuff. And again, 24 slides, we're covering all this stuff. And as long as you're aware of this stuff, you know what you ought to be looking for, right? So far, so good?
So far, so good.
So far, so good. Yes, sir.
So if you have an antenna analyzer which can do open, shorts, and load calibration,
Yes.
you got to do that first and then connect your antenna to your feed line and measure at your rig.
Yeah, right. What you're doing is you're taking the feed line out of the measurement. So you have the feed line connected to your analyzer. You put these 3 different loads at the end of that feed line, the end you're going to hook to your antenna, and you tell the antenna analyzer what you've done, and it's okay. Now I know what's going on. You hook your coax to your antenna, and it'll measure your impedance as if it was right there.
Oh, as if the coax didn't exist.
As if it didn't exist. You've taken the feed line out of the measurement. Remember, I said you gotta learn how to cheat. Pretty good, huh? I think Rick likes that.
Works for me.
By the way, that was slide 16. So here's the way we used to do things. Anybody ever seen one of these? The old standard SWR meter. They sell them for about 90 bucks. This one goes from 160 meters. We all know what those are, don't we? All the way up to 150 megahertz. And it'll also tell you how much power. Sorta. Kinda. In the realm of. We don't use these much anymore. The problem with using this is if you want to measure your SWR, you got to put a whole bunch of power into your antenna, and your neighbor's trying to talk to his buddy. Right? You know how much power the antenna analyzer puts into your antenna?
200 milliwatt.
1 milliwatt. 1,000th of a watt. Pretty good. Some of them might even put 2. Significant difference, so it kind of keeps the QRM down. Anyway, you don't need any of these. So let's talk about the real issues. And these are very real issues. HOA restrictions. That is the #1 complaint of most hams I talk to, is how do I deal with this HOA nonsense? Remember, if they can't see it, they can't complain about it. Here's a really important one. Spousal objections.
Yeah, that one just dumb flummoxes me. I don't, but then here I am, right? Ham already. I should complain.
You've been indoctrinated. You passed the test.
Yes.
You made it.
Apologies.
So in any event, spousal objections is a real problem with antennas. Remember, tomorrow is Valentine's Day.
Time to drill a hole in the wall to run that coax.
Yes. Yes.
If they love you, they'll let you.
And then the one thing that always comes up is cost. Well, yeah, everything costs. That's why you got in this hobby. You had too much disposable income. Have at it. Antenna height. That's always an issue. Available supports. Do you have a 90-foot tower in your backyard? Probably not. If you do, you've already covered spousal objections. You think I'm lying?
I'm single.
Band? Is that due to the fact you had the 90-foot tower in the backyard?
Radio came after.
Band interest. What band you want to operate? If you want to operate only UHF, you don't need a lot of fancy stuff, you know. Repeaters are on the hill. By the way, the repeater didn't do anything fancy. They just took care of the antenna problem themselves. They just put it on top of a mountain. You could do the same thing. You know, you could actually put your shack on the top of a mountain and dial in, right? People do that.
It's becoming more and more popular.
In fact, I was talking to a guy who bought a house somewhere up in Nevada because they already had a tower and an antenna in place. He put a rig there and he rents the house out to people. He makes enough money renting the house that he got a free ham station. It works. There's not a thing wrong with it.
And it's plugged into their power.
There's a, like I said, when in doubt, you got to learn how to cheat. So, band interest, we talked about that. Desired radiation pattern is a concern. Which way do you wish these signals to go? Trying to communicate with Alaska only? Probably not a good idea, but I mean, you can do that. Feed line entry. James hit on that. You know, how do you get the feed line to your rig? That's an issue. The one rule of thumb, out of sight is out of mind. Right? Believe it or not, the wiring in your house and the plumbing in your house and your rain gutters, all that stuff impacts your antenna. Not only that, plant life. We have some crepe myrtles in our yard. My wife is a master gardener. She loves to play in the dirt. I have a dirty wife. So I got a pair of phased verticals in my backyard, and one of these crepe myrtles is right next to one of my verticals. And my antenna one day is not working. So I go over and I look at things, and this crepe myrtle is oozing all this sap out of it. And I thought, aha, I know what's going on here. So I cut off the offending branches. Asked me how popular I was. I did that, kind of cleaned stuff up. My antenna's working like a charm again. So plant life has an impact on what's going on, and that doesn't have to touch your antenna to have an impact. Plants will absorb energy. There's been a number of articles in QST about the effects of plant life. Plants are living things. I used to.
Does radio does the energy affect the plants in a positive or negative way?
It makes them very happy.
They like it.
They grow well in the dark. Ground properties, we talked about that, didn't we? How much control do you have over the ground?
Depends on how much money you have.
You have no control over the ground. In fact, many, many, many years ago, one of the things I used to do when they were putting in these radial systems for these broadcast stations, they'd had all these trenches, and they put it. Broadcast stations were required to have 360 radials. And oh yeah, you talk about buried copper, and they'd go through and they'd treat those trenches with ionic material, so they get better ground conductivity.
Wow.
And they do, and by the way, that's done a lot of times with grounding systems for power systems. For example, powerhouses, when they build powerhouses, where they have those big generators and all that stuff. There's a lot of that goes on, where they actually treat the soil where they put in the grounding conductors. And those grounding conductors, they'd use typically like 3/0 copper, 2/0 copper, and the connections with that copper is all done with exothermic welds.
Oh.
It's all welded together, big grids, and all that's done to improve ground conductivity.
Interesting.
And spend your tax dollars.
So where they just add salt to the soil?
Special salts, yes. There's a number of compounds that they use to do that. We're not going to be doing that. You can if you want, but then the cost of antennas is kind of a meaningless phenomena. So the other thing that will drive you nuts is power line noise. Anybody run into that?
Oh, yeah.
Switch mode power supplies, don't you just love them? Inverters, your dope growing buddy down the street, and all that stuff.
You mean
That's
power,
not true.
All the high
noise
frequency,
What's that?
power line noise in your house or power line noise on the transmission lines in your backyard?
yes.
Power line noise that you see, that you sense within your station. It can come from your neighbors. It can come from, a lot of it comes in your own house, believe it or
Yeah.
not.
Dishwasher or a light bulb or something like that.
It all depends on the appliances.
A lot of
You know, Carol had a new air conditioning system put in her house, and it used a variable frequency drive on the compressor, and it drove her crazy. Because nowadays, an awful lot of these motors, they use these exotic switch mode variable frequency drives to gain efficiency. You know, appliance manufacturers are under the gun to have more efficient products, use less energy. But in that process, it creates an awful lot of electrical noise. So tracking that stuff down is another issue.
So what
Yeah,
about
pipes.
power line internet? Internet over power
Oh,
line?
Internet over power line.
Yeah.
yes.
Broadband over power line is where they actually have, they use the power line.
Power line carrier.
Yeah.
Power line carrier stuff. I didn't know they were doing that. The internet doing that?
You can do it in your house, but instead of running coax or running,
Well, I can believe that. There may be issues with it. I'm not aware of it. I've never run across it. I used to sell a lot of power line carrier stuff. In fact, out here at Aerojet, they had something like a dozen 500,000 square foot buildings. That's a lot of building. And they were doing an energy conservation program. And you know, you get your electric bill and they got time of day charges and all that nonsense. Wilson's the guy that causes all this, by the way. So in any event, the idea was to kind of switch off the loads you don't need, but wiring all those switches in these 500,000 square foot buildings was a major task. Well, there was a company that manufactured power line carrier remote switching, and I sold Aerojet. I couldn't tell you how many tens of thousands, if not hundreds of thousands of dollars worth of power line carrier switching we did. So we had control over those loads. It saved them a ton of money in utility charges.
Yeah, now everybody has Nest.
Nest, I don't know what that is.
Internet connected smart houses where you can turn the lights on and then change the temperature of your house from away from the house and all that.
Don't you have a husband?
If he's in the seat next to you, yeah.
Haven't you got a boot?
When we used to be when we were coming home from work, we'd turn the AC back on so it'd be cool enough to walk in when we got there.
Wow.
On my phone.
Well, there's all kinds of emerging
But,
technologies. And all that stuff has the potential to cause you fits.
Yeah.
And tracking it down is, in fact, I'll tell you another story, and I think Wilson would appreciate this. I thought I had a problem with SMUD's high voltage transmission lines in my neighborhood because I get all kinds of noise. So I bought one of these little parabolic bird listening devices. You know, you got a little plastic parabolic dish and there's a microphone in it. Well, if you take that amplifier and you cheat, remember, cheat is a magic word. If you take that audio signal, because it's almost ultrasonic audio, and you mix that with a lower frequency, and you amplify that into the audio range, you can hear the power lines arc. So it's a classic super heterodyne, right?
Okay.
So I built my own little super heterodyne bird watcher. Doesn't everybody do that? And so you could go down, walk down the power line, yeah, that one's arcing and that one's arcing, and they work pretty well.
Yeah. Yeah. Well, the power line over the internet over power line thing, I think when it was first applied, was used for switching the equipment, being able to switch between nodes and stuff on the poles, right?
Well,
you know what I mean?
I don't know about distribution systems, but in transmission systems, where I work, we did carried out protective relaying over power line.
Yeah. That's been around a long time. That goes back to the 50s.
Yeah.
Still use it.
So anyway,
Question, sorry.
yes.
In terms of obstructions of antennas, I mean, you said plants could cause some interference. Buildings obviously do as well, right?
Yes.
So if I put my antenna up and I doubt anybody's closer to the home versus away, that affects also.
What you need is about 50,000 acres in the desert. and a 100-foot tower is a good place to start. And then, you know, you've got a pretty unobstructed path to wherever you wish to go. Most of us don't have that option, unless you want to buy that house in Nevada I was telling you about.
Yeah, or so you can park next to the ocean and get even
Oh,
better.
that's even better. But yeah, you're exactly right. Everything impacts your antenna. Just understand that. Everything has an impact on your antenna.
So if you hang an element for a half-wave, you know, in-fed half-wave, if you swing it around the tree trunk, that trunk's gonna take some of the energy, right?
Yes, it will.
Yep.
It's better to get it away from the tree.
Yeah, well, sometimes it's better to get it to the top of the tree.
Right.
Yeah,
It's a better trade-off, I think. So far, so good?
so far.
Hey, we're doing good. We're on slide number 19, and it's 7 o'clock. Some comments on mobile antennas. Like I said, everything in that book, we got down to 24 slides. See that little smart car? A ham buddy in Napa did an HF rig installation in his smart car. Now, this same guy was a pilot for the CIA. I said, what did you fly? He said, everything.
Wow.
So he retires from the CIA, he moves to the Napa Valley, and he starts a hot air balloon business. He did that for a number of years, nice guy, David's his name, and he drove around this big fancy Mercedes. And he saw that little smart car, he said, I like that. I want one of those. And of course he had an HF rig in his big fancy Mercedes, so he puts one in this little smart car. It did not work so good.
Plastic?
You know why?
A lot of plastic.
Polymer body panels, plastic, or is it too small of a?
Remember, the shortest resonant length is 1/2 wavelength. So this whip you have on your car is a 1/4 wavelength, and the rest of the car provides the other 1/4 wavelength.
They're only 8 feet long.
The smart car has a plastic body. The other 1/4 wavelength is missing. I told him to buy a 100-foot chain. He thought I was a smartass. He was right. I thought you might get a kick out of that. So anyhow, let's talk some more. Here's a couple of fancy charts I produced. You like them? Mm-hmm. Aren't those gorgeous? That was done in 4NEC, one of these antenna modeling programs. So in any event, the one on the left is a 40-meter dipole, and it's exactly 1/2 wavelength above ground. And you see that green dot, which I don't know why this cursor won't show on the screen. In any event, there's a little green dot up there on the right-hand side. Can you see it?
Yeah. Yep.
Well, that's the radiation angle. And it's about 30-degree radiation angle, and that's about what you would expect of a dipole that's a 1/2 wavelength above ground. We haven't defined where ground is yet. It's an anomaly. You never know where it is. So in any event, I'm going to make this antenna work better. I am going to take it up to 100 feet. Look what happens to your radiation pattern. What happened?
Go straight up.
That's NVIS, isn't it? But also look at the lower lobe. The radiation angle dropped to 20 degrees. So every time you change the elevation of your antenna, you generate these lobes, these extra lobes. Nobody gets a perfect pattern. It doesn't exist.
So these are just theoreticals?
These are calculated,
Yeah.
and the real world will be worse.
Yeah, okay.
But it doesn't matter. You're not so sure where you want it to go anyway, are you? You just say
Not yet.
CQ, right?
Yo, anybody out there?
Am I lying?
Talk to me, honey.
The 100-foot antenna, not only has it lowered the takeoff angle, which I suppose could be may be good if I want.
It's good.
Yeah.
You get two things going on. You get the guys close in, and you get some long distance stuff because of the lower radiation
Am I
angle.
losing a lot of?
You're losing power in both planes.
Yeah.
But by the lower angle, you probably picked up more than you lost with that vertical thing. Again, you know, all this stuff is a trade-off, and there is no perfect solution. I'm just trying to show you what's going on so that you're not stuck like I was, pulling your hair out, trying out, how come every time I make this thing better, it's worse? Right?
Yeah.
And again, we're in a period of time. We've got all the answers. You got the internet with everything you can think of. You got these great tools that sell for $60. You've got these rigs that will do anything you can imagine. They'll run your antenna tuner for you, and they provide a panoramic display. And I mean, we've got all kinds of stuff to play with. So anyway, let's go on. That's slide number 22, by the way. Slide number 23. Anybody recognize what's going on here? What is that? That's what ham radio is all about, by the way. It is propagation.
Yeah.
And they note there that there's an E layer and an F layer. And then they got these color codes, what happens at low frequencies and medium frequencies and high frequencies and VHF, UHF stuff. You note that the VHF, UHF stuff penetrates all those layers. It goes straight up. And then as you get down into RHF world, you get some reflection off both the E and the F layers. And so that radiation angle we're talking about, where it hits these layers, that determines how far you're actually able to communicate, because it's a mirror. It's effectively a mirror. It takes your radiated signal and it reflects it back.
Thanks.
And depending upon the time of day, how much sun's impacting those layers changes your propagation. See how magical this stuff is?
Oh, okay.
You guys didn't know you knew all this stuff. So anyhow, it just,
Okay.
and that explains why things fade in and fade out, doesn't it?
Yeah.
In my case, it's when I get too sleepy.
Yep.
That's a pretty good story. So in any event, propagation. It's all dependent upon the ionosphere and at what angle your signal hits the ionosphere. Question?
Is a higher angle preferred or a lower angle?
Lower,
Lower.
for distance. Now, in the case of working close in, we like this term NVIS,
Yeah.
cloud warmer. Because now everybody around you within about 100 miles, it works really, really, really well.
Cloud warmer?
Cloud warmer.
That'll make it rain.
That's tomorrow. And by the way, do you know what a mess rain does to a golf course? Bob Mix and I have been trying to play for the past 3 weeks, and we come home with mud everywhere. It's disgusting.
Take up a new hobby. Mountain biking.
I used to flat track motorcycle race. Is that the same kind of thing?
Similar.
Almost.
Still on the NVIS. It would seem to me, without using the model, that the lower my antenna is from ground, the more.
It's exactly right.
NVIS.
That's exactly right.
But you, on that chart, it looked NVIS increased when the antenna went up.
That's kind of remarkable, isn't it?
Yeah.
You wouldn't expect that, would you?
No.
Now, if I had made it exactly one wavelength high, we'd have had about 3 lobes, and that middle one wouldn't have been nearly as high. I mean, it all depends upon where you position that antenna. Relative to ground, which, by the way, we don't know where ground is, do we?
So,
Isn't that crazy?
so somebody
You
that
think
has-
you know.
Yeah, so somebody that has a crank-up antenna can vary the distance that they get by moving the antenna height.
They can do that, absolutely.
The takeoff thing.
I mean, yeah, because I
Yes, it
always
does.
thought about it was relevant to being able to get out to mount it.
But a better idea is to lower it when the wind's blowing.
Yeah, there is that. Yeah.
All right, so let's go on. We're going to go to the last slide now.
Can I just say one thing that's
Absolutely.
maybe of interest? I'm emergency communications and the military use NVIS quite a bit for nearish communication.
Yes, have been doing that forever.
Yeah.
That goes back to World War II. Remember I told you that a half-wave dipole at a half wavelength above ground has a characteristic impedance of 72 ohms. You see this chart, which by the way is in that book. You see as you go down 0.0, 0.1, 0.2, and you get to 0.5, you see how there's a dip there? And if you read across over on the left, you'll see it crosses right where it says 70. So as you vary the height of your antenna, the characteristic impedance changes.
Huh.
So not only does it affect the propagation, it affects the input impedance.
Oh, so when you do run the tower up and down, you're going to detune
You're
for
going
the
to
frequency.
well, not necessarily. You haven't changed the resonance point, although that can happen too. But it changes the characteristic impedance, which as long as you stay under 20% reflected energy, it's no big deal.
Okay.
The other guy on the other end probably wouldn't notice any difference. But these are studies, and they're well-recognized studies. They're in the book. How many pages in that book?
40?
I think there's more pages.
More than
How many pages, Gert?
Bunch of blank notes. Oh, come on, give me a number. We don't number the index.
I'm guessing around 1,200.
Oh, no, this is an ARL book.
Oh,
it
so
has,
we got
26 chapters, page 1, 2, 3. You know.
the bottom line is there's a lot of stuff in that book, and all these things we're talking about are covered in that book. But the stuff I showed you will cover 99% of the issues you run across. By the way, does this stuff that I talked about work on VHF?
Yeah,
Same stuff, isn't it? How about UHF?
yeah,
Same stuff. How about 160 meters?
yeah.
It's all the same stuff.
It's just math, basically.
It's just physics.
Yeah, well.
It's just physics, you just solve the problem. This is the last slide, and it's 7:20.
I have a question.
Absolutely.
You touched on it, but how important is the coax I use, particularly for HF? Should I use LMR 400? Should I use RGA? And should I be worried about the losses in the coax, even at the HF range? Because I think we all...
The answer is every piece of transmission line has intrinsic losses. The transmission line with the least losses is open ladder line. So from the standpoint of which one to use, in most instances the one that you want to use is the one you can afford. So LMR 400's at the high end of the list, right? Open ladder line's relatively cheap. You can make your own, believe it or not. Open ladder line. Again, guilty of a lot of that stuff. It fascinates me. So, you can use open ladder line. It's a pain in the fanny to route it into your shack. You have to do some manipulating. But from a practical standpoint, the higher you go in frequency, the better feed line you need. Now on 40 meters, if you're going to your end-fed half wave, I would think that 240 stuff, it's roughly a RG58U, would probably be more than adequate. In fact, I've got some examples here we can get into, whatever you guys are interested in. I built a horizontal J-pole for 80 meters. Anybody want to believe that?
Is that the one on your fence?
Yes, it's on the fence. 6 feet high, by the way. An 80-meter J-pole. And so when I first built this 80-meter J-pole, I took a model of a 2-meter antenna, I scaled it up, I built it, I find the right tap point, I had it resonate at 3750 at an SWR of about 1.05 to 1. Now who's going to believe that? I've got pictures, I'll show you. So I got to thinking about that one day. Do you know what constitutes a J-pole? Think about the days of the dirigible. You know, those big old flying balloons? And they needed to talk to the tower. The problem was, in those days, they communicated at frequencies down around the broadcast band, so you needed a really, really long antenna. Well, how do you feed a really, really long antenna in the middle when you're flying? So they were the originators of the end-fed half wave, the dirigible, which they called a ZEP. Okay?
Ah, that's where the term came
That's
from,
where
that
that
one.
came from, right. So what they would use is a piece of open ladder line, something similar, with an antenna. The middle of the antenna is the low impedance point. The ends of the antenna are the high impedance point. I didn't go through that, but that's how it works. In the middle is low impedance, the ends are high impedance. In the middle is the high current, on the ends is the high voltage. So far, so good? So they're trying to feed this antenna, so they say, well, you know, the simple thing is, if we use a quarter wave piece of transmission line, remember we talk about quarter wave lines? Quarter wave length of transmission line, when it gets to the antenna, it's at the high voltage point. And then the wave dips down in the middle of the antenna, it'll be the high current point, and the other end of the antenna will be a high impedance point again. Work like a charm. So, in true dirigible fashion, you like the way I said that? True dirigible fashion. I decided, well, you know, all I need is a quarter wave transmission line. I don't need this open ladder line. So I go rummaging through the garage, and I got a roll of RG6U TV coax. Now, who uses RG6U TV coax with FEM antenna? I did. So I cut a quarter wave length of RG6U, hooked it to my antenna. I cut out that open ladder line, and then, you know, at one end of that antenna, it's 0 ohms, but I want to feed it at 50 ohms. So I put a tap in the middle, you know, like 10 or 12 feet from the end, and I measured the impedance, and I got to 50 ohms, and I fed it with a 50 ohm piece of coax, and lo and behold, SWR 1.03 to 1 at 3750, and it worked just as well as that open ladder line. I thought, well, I'm a pretty smart fellow. And then I got to thinking about it later. See, there's a pattern here. You're going to pick up on it pretty quick. There's a pattern here. You know, one day I'm thinking, you know, in this day and age, everybody's doing this end-fed half-wave stuff. Well, I got a half-wave antenna. I tried the open ladder line match thing. It worked pretty good. I tried the RG6U, and it worked pretty good. I'll just wind a transformer and see how that works. Guess what? 1.04 to 1, 3750, and it worked just fine with one advantage. It also worked on 40 meters, and it also worked on 20 meters. So, you know, this stuff, you can play with it 912 different ways as long as you stick with the principles. And it worked like a charm. Still warms the clouds because it's 6 feet off the ground.
Is there any loss when you use the transformer versus using your transmission line normally?
You know, I would suspect, now we're clear down at 3.5 megahertz.
Right.
I suspect that the loss in any three of those, and all three of those, was pretty minimal. A couple of dB. I never bothered to measure it. But yeah, there's a difference in the losses. But I don't know what the difference was. I never bothered to calculate it or measure it. But it works. So what other questions you guys have?
Question on the impedance and the chart over there, and the impedance changing. And you said an antenna tuner matches impedance, right?
Yes.
So if I use a tuner,
Yes.
this should compensate for,
Absolutely.
what does it make it flat?
No. Your antenna tuner corrects for one frequency.
Yeah. Okay.
So if you're operating in the middle of the band, you'll adjust the tuner to keep it under 2 to 1 there at the middle of the band. But as you change frequencies within the band, you'll find you have to adjust that tuner. And it's true of everything. Now, it's back to what we said at the very beginning. SWR 1.0 to 1 is good at one frequency. The beauty of the tuner is you sit in your shack and you adjust it. Now, there was a question several years ago, no, not even that, about a year and a half ago, at a club meeting. It wasn't this club, it was a different club. A guy asked the question, what are the losses through an antenna tuner? Well, I didn't know. So what we did is we took 2 antenna tuners, identical tuners, and we adjusted one of them to match what he was to match what he was using on his antenna. We took a second one and we sent it exactly the same way. So we took the rig, went into the tuner, out of the tuner to the output of the other tuner, and then out of the input of that tuner we went to a power meter. Would you like to guess what the losses were? 15 to 20 dB.
Wow.
It was pretty efficient. I was surprised, actually. 15 to 20, but it depends upon how big a match adjustment you make. So there are losses. There's always losses. The beauty of it is, if you're able to talk to your buddy, they're not insurmountable losses. If you can't talk to your buddy, get a new idea.
0.15 or 15?
No, it's 15.
15. That's
About 15. No, it was. No, it's 15% loss. 15%. It wasn't dB. 15% loss. dB is a whole different world.
Yeah, I was going to say 15 dB seems a little bit much.
It would be a bit much. Yeah.
Yeah.
I'd be interested to know who's in the process of setting up a HF shack, or have questions. Alan, how's that going? What are you doing?
Well, I could talk about myself for the rest of the meeting, but
You have the floor.
and I have lots of questions based on what you've said here today.
Well, ask them.
I did not buy a resonant antenna. I bought a end-fed long wire. Should I take it back?
Does it work?
It works good. And it has a Fallon or a
It's a matching transformer.
or a matching
Yeah.
device.
Yeah.
So that's what really makes it work.
Well, so the first question is, what frequency is it resonant at?
Well, it is designed for 160.6.
That isn't what I asked.
Right, it probably isn't what you asked, but now...
What you're telling me is you don't know.
Well, I'll try to figure that out. And it leads to other questions that I have, too.
Do you have an antenna analyzer?
I am a proud new owner of a NanoVNA, the H4, the brand new one, a little bit bigger screen. And when you're talking about that unit, you say to calibrate it with open, short, and low.
Which comes in the kit.
And I know how to do that with the, it comes with the kit, these little devices. I watch YouTube, I know how to do that. But you said you have to do that out at the antenna.
No, at the end of the feed line.
So you disconnect the antenna, right? And then put the shorts on the end of the feed line?
You actually put the short, the load, and the open on the device. And you press a button and you calibrate.
Yeah.
Then you take the antenna feed line. I mean, correct me where I'm wrong.
Well, stop right there, because you don't need to calibrate the unit by itself. because you're not going to measure anything at the end of the unit if you need to do it at the end of the feed line. You can make your open short load calibration at the end of the feed line, period.
You're changing the reference point. So instead of the reference point being at the NanoVNA at the port, you can move it to the end of your coax where the antenna is at.
Where you're actually going to connect the antenna. That's where you want to make the measurement. You want that NanoVNA to measure the impedance at the antenna. Now, if you take the NanoVNA to the antenna, you've done that, and that's where you would calibrate it at the port of the NanoVNA. You're giving me
I'm
the.
lost on the NanoVNA and what we're saying here. I'm very interested also, and you said you gave some classes. Are those available?
We did a one-time deal.
Oh, okay.
And we feel it's like tonight. Every time we do something like this, it's an overflow crowd. So we'll probably redo the NanoVNA thing. Our challenge, frankly, is finding a place to hold the meetings.
So can I express kind of what my experience has been? I started off.
You go right ahead.
I started off, cutting wire, making my own dipoles, and they worked. But I didn't really understand the full scale of the coax and how it impacted the antenna and everything else that was going on around it. And after so many experiments and homebrew projects and stuff, I got to a point where, because I don't have a lot of time to tinker and experiment because I have a lot of obligations, with work and family and stuff. So I said, anytime an antenna works, that's good enough for me, I don't need to know.
That's a pretty good answer.
Personally, I don't need to know what the SWR is or whether or not it's efficient. I'm talking to my buddy over there, and that's all I really want to do. So
Mission accomplished.
I got all the tech equipment in the background and everything, but I'm like, if that antenna's working for me today, that's all I need. I don't care if I can't talk to them.
And I hear that too, but we're all technics.
Yeah,
we're all
that's
here
true.
to geek out.
That's
so
for sure.
How else can you geek out unless you have one of these devices,
Absolutely. And I've got mine, and I can do it, but it's like, I put in a new antenna the other day, and it just works. And I'm like, you know what? I don't need to know anything else right now.
Yeah. That's a perfectly acceptable answer. Where the problem comes in is when you end up with this blank stare on your face.
Yeah.
You think you've done everything right, and it doesn't work. And you're trying to figure out why. So, back to your point, the one thing you need to recognize is all of these antenna analyzers are pretty much the same thing. There's a little microprocessor in there that runs some high-level math, and it's there to measure impedance. It doesn't really measure SWR, it measures impedance, and then it tells you what the SWR would be based upon those impedance values. And again, remember I was telling you the $20,000, $50,000 Hewlett-Packard stuff? It was all about measuring impedances, and that still goes on. So, it's the calibration point that matters with any of these analyzers, any of that high-end equipment. You tell this fancy computer where you're making the measurement, and you tell it that by doing that open short load calibration at that point. It can be at the analyzer, it can be at the end of a 50-foot piece of coax, it could be at the end of 1,000 feet of coax if you don't have too many losses in the coax. The analyzer will give you an accurate reading based upon where that calibration plane is. And in your case, for your end-fed wire, you want it at where that coax attaches to your antenna. You want to calibrate it there.
Go up at the roof.
It doesn't have to be at the roof. You can calibrate it on the floor and take the coax to the roof.
Oh, okay. I think he's saying he's got to go up on the roof and detach it and bring it down where he can work on it.
And so you could add those parts to the end of it for each part of the test, but so you could pull it down out of the air and just do it on the grass or whatever.
And I don't understand how I physically do that because these are little tiny.
They're SMAs.
And stops. And
Yeah, they're SMA. You need adapters.
There's a jumper key.
You probably got PL259 connectors on your coax.
Right.
So what you need is an adapter that allows you to use SMA connectors with your PL259. And if you go on Amazon, they got them. I mean, everybody else has got them too.
You know, some of
HRO has
the
them.
NanoVNA kits come with those adapters.
Depending upon which one you buy.
Adapters too.
You know, it has a PL259 female on one end, or
Well, it depends on which model you buy.
Yeah.
So in any event, you just need the proper adapter. And you're gonna, I've got a case this big filled with various adapters. Every time I go to a ham swap meet, I rummage through and find a few more to throw in there.
Yeah. The antenna
Well,
works.
you never can have too
I hear
many.
these voices coming out of my box, so yeah.
Have you tried to talk to somebody yet?
Yeah.
All right.
Yeah.
Does it work?
It works. My question, I guess, is
Oh, Wilson,
I
got a
have
picture.
those. That's not my question.
Oh.
And I'm not very articulate and a beginner here. But, I forgot what I was going to say.
So
Me too.
You're drawing this on the board. You're just testing your coax first.
Right. Well, what I'm doing, the instructions as I understood them from my YouTube Elmer was to calibrate the unit. And you're saying that doesn't matter.
It does
It
matter.
shows you how to calibrate the unit with the open short.
That's fine. Yeah.
And then I
Right.
that's done. The unit is calibrated. I take my coax with the adapter, put it in there, and I can get the curves.
Well, sure you get them. But that doesn't mean it's the right curve. The only thing what you've got to do is you have got to position your antenna analyzer at your antenna to measure what's going on with your antenna. Now there's two ways to do that. You can take the analyzer to the antenna once it's calibrated, and that's exactly what you were talking about. You calibrate the unit
Okay,
and you measure the antenna.
that's what I do.
That's fine. If you took that up to where your antenna is and made your measurement,
I could do that.
that's perfect.
Yeah.
That's perfect. The other option is to calibrate out the effects of your transmission line, which is why you do the calibration at the end of the transmission line. The box is smart enough to accept either answer. It doesn't care. It has the ability to adjust for your transmission line. And we went through this several times during our NanoVNA thing. And James, I'm beginning to think we're going to have to do this again.
I would appreciate it.
I'm thinking so.
That's a
Maybe
good class.
depending
Very
on,
good class.
you know what, this is a 3 workshop seminar. This is workshop 1.
Is it 3? Yeah.
But we're thinking, we want to do a 4th in a park or something, and maybe we can do a demonstration, maybe not teach it, maybe do a demonstration.
No. You have to do this as a hands-on.
Yeah. And
You have to do it as a hands-on.
yeah,
Can I
watching
try
somebody.
to kind of add something to this?
You go right ahead.
You know, your coax is kind of like it's a transformer, which means that for everything you do, it affects the measurement. If you change the frequency or the wavelength, whatever. So what he's talking about is you want to make it invisible to the measurement. So that's what the calibration process is going to do for the unit. It's going to kind of mask out the coax, make it as if you're standing right there with the unit.
At the antenna?
As if you were there, except it's...
But I'm at the coax.
You're at the other end of the coax in your shack, on the other end of the 100-foot of length coax.
50 in my case.
Whatever, but
Yeah.
what you're doing is it's kind of like subtracting it from the mat.
Yes.
Subtracting it out, and it's invisible when you measure when you hook it back up to your antenna and you measure.
There's a magic word for that, by the way. De-embed.
De-embed.
De-embed the transmission line
And
from your
then what you can
measurement.
do is now when you start tweaking the antenna, you're just isolating it to just the antenna.
So now you're standing on the roof, testing the antenna with nothing in between.
Right.
It's exactly the same thing as far as the analyzer is concerned. You get the real answer. Otherwise, you're up in that attic with me cutting wire and splicing wire and trying to figure out why it doesn't work.
So there's another example I know about. Bob, do you want to talk about what you've been experiencing with your buddy pole?
Yeah, my buddy pole has been, we can't tune it in on 40 meters. If I tune it in to what the chart says from Buddy Pole, I've been getting an SWR of about 10.
Oh, good.
Ouch.
Well, let's talk about that briefly. Does Buddy Pole know anything about the ground in your backyard?
No.
Exactly. Does Buddy Pole know anything about the wiring in your house, the rain gutters, the neighbor's cyclone fence? Probably not.
No, but when I put it up on 10 meters, I get a SWR of about 12.22, and it's been traveling. I mean, I've been getting some good readings out of it.
Again, remember I showed you this slide. Hang on a second here. If I can figure out how to get where I want to be.
Oh, I did find another chart, and I unpinned it. I didn't use any.
All right, these charts here, these two that I got up on the screen. See the one on the left? You see where that hyperbolic curve dips down?
Right.
And that little arrow is? That is the resonant point of your antenna. Do you have an antenna analyzer?
Yes, I do.
Okay, so hook it to your antenna,
I do.
and wherever you think the taps should be for 40 meters, and see where that resonant point is. And if the resonant point, say you're trying to do 7.15 and you're getting 6.9, that means your antenna is too long. Now with a buddy pole, there's loading coils.
Right.
So it means you've got too much loading coil connected. So take 1 or 2 turns out of the tap you have set for your buddy pole. And if it comes up that it's resonating at 7.7, that means your antenna is too short. You need to add more loading coil. That's all you have to do. Antenna analyzer, again, right at the feed point, not through the coax, right at the feed point of the antenna. Find where that resonance point is and adjust the number of taps on your coil, and you'll have a resonant antenna.
Well, I found with the buddy pole too, say if I had the RigExpert hooked to it, then I go over, I had the wife go over and bring it in a little bit. Well, it radiates a whole different reading.
Yes, it does.
So
Which is why you do your open short calibration at the end of the piece of coax, so you can stand 15 feet away and make your measurement, because then nobody's in the path.
Okay,
That's why there's the open short load calibration.
haven't done that.
Yeah, that's what you want. That's what you need to do.
So when your wife was in the antenna area, it affected your measurement? Yeah.
Now, if you
A building affected, I was up at San Juan Bautista this last weekend, and I was right alongside the building on 10 meters, and it was up over 4, and as I brought the pole up away from the building, it dropped right back down into range where I could use it.
exactly what you'd expect. Now the thing is, if you can train your wife to crawl on the roof and make those adjustments for you.
I'll let you answer.
Carol is very reactive.
Honest to God, this open short load thing I'm talking about is essential to being able to use that antenna analyzer to answer your questions.
We might have to, if you're open to it.
Well, I'm happy to do it.
We might need to do it.
But the thing with the NanoVNA, you not only are able to do these antenna analyzing things, but you also can do measure and loss in your coax. You can measure filters, filter performance, all sorts of reactive measures, everything you can possibly manage. And we did that we had, I think it was 2 3-hour sessions. We covered all aspects of using that NanoVNA, and it's all hands-on. We actually had you build a matching network for a random antenna that I configured, so that you could work these examples. And I showed you how to use this tool called SimSmith, which makes all these calculations for you. It's pretty neat stuff. So again, we're probably going to have to do this again.
Yeah.
I'm kind of a one time kind of guy, you know, come up with some harebrained scheme, and we'll do it. And I think, okay, that's enough of that. Let's go find something else to do.
It's been a while, though. You can try it again.
I could try it again.
You know,
Yeah.
kind of like Billy Joel at Madison Square Garden. You just got to keep showing up.
Oh,
It was a compliment.
Yeah.
oh, I don't know how to play a piano.
Phil, can you make your own load and short with like a...
Yes, you can.
I don't want to use adapters, so I just make my own with like a resistor.
Here's the problem. It takes into consideration all these parasitic effects. You know what parasitic means? There's something you want, and then there's something that's hanging on the side. The thing that's hanging on the side we call a parasite. Literally, that's where the term comes from. The problem is these calibration standards are machined to very, very tight tolerances so that you don't have any parasitic effects. So you want to use real open load short calibrations, and you want to use that with connectors, fittings, adapters that are also constant impedance. They're all designed to work in that 50 ohm environment. Now at low frequency stuff, you know, 40 meters, 80 meters, it probably doesn't make a significant difference. But you get up into 20 meters, 15 meters, 10 meters, those effects become very pronounced. So you're better off to do the adapter thing, much better off.
So you're saying even the adapters are calibrated?
Depending upon who made them. You know, if they're Okinawa Mama, maybe not.
Well, Okinawa I trust at Shanghai.
Well, yeah. Yeah, there's a difference in the quality of these adapters. But honest to God, open load short is the greatest thing since sliced bread. What else we got? Question.
I have a metal tiled roof.
Oh boy.
Good, bad, or ugly? I guess I want to know. So I haven't hung anything up yet, but do I need to keep it away from there, get it way up high, or it's not even good?
It's got a heck of a ground plane.
The real answer here is, and I've said this all along, it doesn't matter what's around your antenna, it has an effect. Everything has an effect on your antenna. Now, if on your roof is the only place you can get some elevation, that's probably what you're going to have to use. And try and keep your antenna as far away from that roof as you can. You know, if you can get 10-foot clearance off your roof, that's probably pretty good. 2 foot's probably not so good.
Yeah. Question. If he was doing a vertical, would a tin roof act like a radial system?
If you have radials laid down on top of that 10-foot roof, it won't hurt a thing. It will have a positive effect.
Okay, but
because you've actually configured what's called a counterpoise, and it's more effective reflective surface. But if you're doing a dipole, it probably will have an effect. And there's one other thing that I didn't mention here. Several years ago, I thought I'd be really clever, and I built an 80-meter dipole that hit under my eaves, you know, follow the pitch of the roof. I thought, you know, that's a pretty good way to get up an 80-meter antenna. They can't see it, right? Remember, if they can't see it, they can't complain about it. So I put it up, and lo and behold, that thing resonated like 500 kilohertz under where I thought it should be. That's because the antenna was so close to the ground. It's the capacitive loading of the antenna to the earth. So I had to shorten, I think, each end of that antenna like 15 feet. Maybe even more than that. And then, of course, you get it to resonate. And, of course, the feed point impedance is a little low because you're so darn close to the earth. But, you know, all this stuff can be adjusted. And that's the other thing that we did in this NanoVNA class is I taught you how to make these measurements and build a matching network. An antenna tuner is nothing more than a coil of wire and a capacitor. That's it.
Okay.
And so when we did our clinic, we plugged in various inductors and capacitors and we get a perfect match. Not just close, I mean perfect.
Okay.
No problem. We're gonna have to do it again.
You built all those antennas.
I'm sorry?
I mean, you put all that together, it'd be great to do it again.
Yeah, we'll have to do that.
Are all the toys still in this?
But again, finding a place to do it is the challenge.
Yeah, that's been.
You're all welcome to my house. There's no,
All of them?
there's no wife. Come on.
All of us?
All of you. We feed us all.
Who else has, no, Amy, do you have any questions?
No, Alan.
Yeah.
What else? There's got to be more questions.
Is there?
Sorry, I've got an opportunity to run an antenna from the peak of my roof, maybe another 10 feet up, to a large oak, about 60, 70 feet away from the earth. I can do like a slack line between the two. And I'm wondering if orientation of the antenna matters. This almost completely horizontal, or if it's closer to 45.
You can route that thing any way you like.
I figured if you're putting
And the reason I say that is some antenna is better than no antenna. Okay?
Kind of like
The
our-
only thing that happens is that the radiation patterns change as you change these elevation planes. That doesn't mean it's any better, it doesn't mean it's any worse, it just means it's going to be different. And so my experience is if you got a way to do it, do it. And again, you need to match it so that it performs on the band that you wish to use it. And in your case, you probably are better off with an end-fed as you would be with a dipole. But they're both really the same antenna. It's a half-wave radiator, and whether you feed it in the middle or you feed it on the end, the radiation pattern is exactly the same. It's just which is more convenient for you.
Can you wrap, so Kishore, you wrap an 80 meter end fed,
Yeah.
130 feet of
Yeah.
wire. How long is it?
Yeah, 132 feet.
All along, you're turning, you're
Yeah.
wrapping it, and it works really well.
Yeah, I can tell you kind of what I did. I was
Yeah.
playing on the bunny pole
Yeah.
for 3 weeks on
Yeah.
40 meters. You know, the short whips, the
Yeah.
long whips, the coils, the height. You go nuts with it, right?
Right.
So, I think what I did is, talking to Bob, K6DCN, he said, try an end-fed half-wave. And so I figured out that I can eventually get from the balcony where my feed point is, I can route it to the fence. So it slopes down a bit, and then I can put it up on a sort of temporary pole, not 12 feet pole, but I can take it laterally along my fence, which actually have a metal fence in the back, right? And then loop it back up so it's like a flat U, goes back up into a tree, and it works great.
I rest my case.
Well, when we do field day, we do all kinds of strange things, grabbing trees to hang things off
You don't have
of.
to worry about getting the feed point in the middle of it, because that's the big challenge, right? If I have to get the feed point in the middle, I gotta route my feed line all the way to the fence, right? This is just.
That's why the end fit is such a popular design.
just gonna chuck wire on the roof.
Yes.
Or just go on the ground.
Yeah.
You can talk to your buddy.
I'll tell you what doesn't work well is when you put up a tower and it's stormy day, you go out dirt bike riding with your buddies and you come home and the tower crashed and destroyed the neighbor's fence. That does not work well.
Been there, done that, huh?
Had a great time on a motorcycle though.
What if you have a 1,000-foot tower and you lose all your power in the feed line as it goes up 1,000 feet?
Yeah.
I just turned on the game.
Bigger amplifier.
I do have a question on my antenna, though, right? It's about grounding. See, what about grounding my rig? What about, I mean, it's supposed to ground it, and the end fed, it says it doesn't
So
need
there's
to be
two
grounded?
kinds of ground, and Phil's gonna talk about that
Later on?
right now.
Well, Phil, are we going to address ground?
Let's talk about this.
It's a good question, like what should, it is an important question.
You know,
My antenna says don't ground it.
let's talk about this as a real subject. Picture, if you will, you live in a hot air balloon. And you put up this dipole antenna and you feed it in the middle, and you've got great coverage. Everything works fine, your antenna's resonant, you talk to everybody in the world. Where's your ground? You don't have one, do you?
DC ground.
You don't need one. Now, ground, according to the National Electrical Code, where do we get into this? The National Electric Code requires that you have this service ground. Do you know why? Wait till you hear this. This will make everybody in this room happy. When they first started selling electricity in this country, somebody came up with a bright idea that for purposes of lightning protection, they would take the center tap of the utilities transformer and they would ground it so that lightning couldn't cause too much damage. That's the reason they did that. From that point forward, we started electrocuting people in the bathtub. You know, doing their hair over the sink. And so we've gone down this road with a grounded system since, what, the 20s, the 30s, the teens, I don't know what. But the only reason that they did it in the first place was lightning protection for the purposes of the utility. You go to Europe, there's 2 wires. Neither one of them is ground. And they seem to dry their hair just fine.
They're also using 240.
Right. You only need 2 wires. It doesn't matter what voltage is on the wires, you only need 2 wires. So the bottom line here is electrical grounds for the purposes of the National Electric Code, that's one thing. A station reference ground makes sense if you live in a place that gets a lot of lightning. There you've got some real issues. We don't have that issue here. So I don't get too excited about it. I think it's kind of an over-preached topic of little relevance in our world. So I wouldn't worry about it. It's not going to hurt anything. But it's not something that makes my heart go pittity-pat.
Well, so Phil, I'm trying to make a distinction between electrical ground and RF.
RF ground's a whole nother issue.
Yeah.
Which has nothing to do with antennas, by the way.
That's the next class.
Okay, so if we're not talking utility and we're not talking antenna, so what's with the RF ground?
Well, it's all about shielding.
Okay.
It's all about shielding. As you get involved in some of this stuff, this is such a strange world. It all revolves around physics, and there's these things called circulating currents that you can run into. There's this thing called ground loops that you can run into. All sorts of exotic stuff. And ground in every one of these instances is something different. They all use the term, but they're all different parameters. But from the standpoint of our topic of discussion, which is antenna systems, I would not get too excited about grounding. And if you want to do grounding, it will not hurt a thing.
Okay.
If it makes you feel better. Again, the major concern with grounding and antenna systems is something to deal with lightning. Okay?
On the, say, a long wire you run out, how critical is it to make it turn as a right angle or a nice slow angle if you're going to cross one fence line and then down another fence line?
Have you got a framing square? That's a joke. It's a bad joke. It's not critical.
It's not.
It's not critical.
I was told it was. So.
You know, in our world, first of all, recognize we're all neophytes, right? And you'll be told a story from a very reliable source. By the way, I'm not a reliable source, so and pretty soon you start believing it. Well, the problem is, what do you have as an alternate reference? I mean, think about it. I mean, this is a common practice. You go with a common practice, don't we?
Yeah.
But Harvey Electron doesn't care.
Oh.
He's going to radiate no matter what. You can check with James Clerk Maxwell, by the way. He's the guy that came up with Maxwell's equations that deal with these issues in a mathematical manner. It doesn't matter. The only thing I'll tell you about antennas, you need to be a little cautious, especially about the end of the antenna, because that's a high voltage point. So you have to make sure that you have a tidy insulator, because you don't want your wife, when she's out pruning the roses, to get zapped. You will be in the garage with the dog.
Yeah.
Bringing up the wife, I got a question. Am I gonna be able to get home and call you and you're telling my wife I'm supposed to cheat?
Not one chance.
She might take it the wrong way.
You're dog meat. I'm going to tell her, I don't know where he came up with that crazy idea.
Who else is working on an install or have any questions about it?
Working on an install, but I have the same questions about metal roofs, and so it's raining. It's the rainy season, so I'm not up on my roof doing this. But, I'll get there.
What kind of antenna were you thinking about putting on your roof?
Well, two. So I have a J-pole for UHF VHF, and then end-fed half-wave for the HF.
End-fed half-wave.
Yeah.
But you're going to route that from your roof to something else, I trust.
I could, or I could mount it above high enough. I guess those are my questions about how the metal roof impacts, antenna performance, or can you use it as a counterpoise, like you were saying?
You can model that. And there's some great software out for doing that. I don't know. It'd be interesting to see. Frankly, if it were me, if I had the further you can get one end of that antenna away from your house, the better off you are, because it's got open space to radiate and the pattern is less impacted.
Right.
And if you can do that, that's the smart play as far as I'm concerned.
Yeah, similar to Chad, I have a large tree that I can probably just put the one end.
Perfect. Absolutely perfect.
And the high voltage end away from the house is probably a good idea anyway.
Both ends are high voltage.
Yeah, but that one's going to control space where it's attached, but the other end.
If you have a neighbor who's really, really helpful, you can have him hang on to one end of that antenna while you test it.
You play with love.
So we have a couple examples of long wires coming near fencing at 6 or 8 feet high, and then kind of coming off the fence. Should the wires touching the fence? Like, Rick, are you laying it on top of the fence?
Is it a metal fence?
No, the wood fences. And I was going to put up a pole and run it from the top of the pole.
I have, somewhere in here, gosh darn it, where am I here? I want to go in here, and I want to go in here.
You want to make sure.
I was going to say, electric fence insulators aren't a bad idea if you're mounting it on a fence, just because it suspends it.
That's not what I want.
I
want.
It's going to be high on both ends, but you want to make sure, you guys, with safety, it's also in that book. You don't want your antenna in an area where somebody can put their hands on it, or a kid or something.
What about a squirrel?
Squirrels are fine.
Barbecue them suckers.
How do you like your squirrel? Well done.
You can get very bad RF burns.
All right, so somewhere in here,
Wilson is N6EMF intentionally. Wilson knows all this.
Remember I was telling you about my,
The crepe myrtle?
you see that insulator there? All that is a piece of 1.25" PVC. I drill a hole through this way for the antenna to go through. Then I drill through this way for the screw to go to the fence, and then I make the hole you're looking at bigger so you can get the bit in to drive the screw into the fence. And that keeps your antenna wire off the fence. It's a cheap, fast, easy, effective fence insulator.
That's great.
How high off the ground is that?
About 6 feet.
What kind of wire is that?
Whatever I had in the house. I think it's 18 gauge.
The wire goes through the center of the
Yeah.
insulator.
Yeah.
Keep
Now,
it off the-
remember I told you I had the ladder line? Well, this is ladder line. To the right is ladder line, and then the radiating element goes off to the left. Let's see. Yeah. See, here's where I was doing it with the ladder line for the feed point. This is where I scaled the J pole, the horizontal. So the radiating element's 136 feet long. The matching section's 61 foot 9 inches. And it worked. And so here's where the feed line is. See how I tapped that ladder line I built? And this is where you transition to the actual element. These are the insulators. Here is the pattern. Notice everything's going straight up.
That's because it's so low. Right?
There is the SWR curve. Point 1, it's 1.25 to 1 at 7.569 megahertz. And the bandwidth is 3.71 to 3.81. So I got 100 kilohertz bandwidth on 80 meters at 6 feet off the ground.
How do you run your feed line from that? Is it just on the ground, or do you
Well, I'll show you.
go straight to your house?
Oops, went too far. That's my, oops, stop. That's my feed line coming off of there, and I went into the house off of that.
Okay.
That's just the tap.
Underground or?
I think actually did. I had a conduit that went underground and then up to my shack.
I was picturing with all the gardening that's going on, you don't want to
Oh yeah.
hanging out.
Oh yeah. What else we got going on here?
How do you choose the distance between the parallel wires?
In the ARL handbook, there's a table that shows you how to calculate the impedance of parallel ladder line. I made that calculation.
You know, his question about turning the sharp right angle and versus the curve might have had to do with the capacity, you know, the
Yeah.
inductive kind of
Inductance.
effect from that being, you know, fairly close.
I wouldn't worry about it. Was there something else, another topic, question, comment?
I was going to say something though. You know when you take a piece of wire and at the end of the antenna wire,
Whoa.
use that extra length to sort of turn it back on itself
Yes.
and wrap it around, you know, itself.
Okay.
Rather than cut it, right?
Yeah, rather than cut it,
Yes.
that section just disappears. It just kind of
Yes, it does.
part of the length
Yes, it does.
that is folded back on. So I think if you kind of extend that conceptually to a tight bend, you might get close to having some of that length disappear, but it probably
Measure
doesn't
it.
matter.
See what it does.
Yeah, but at right angles it'd be like the inverted V. It's actually not a real issue, now that I think about it.
No. Remember I was telling about my phase verticals? Those are my phase verticals. So this is the fence. You can see the fence. And what I did is I used a piece of, I think it was 1.25" PVC up against the fence. And I think in my next slide,
So
here it's modeled. I'm
we
sorry.
didn't cut those whiskers off the top.
Well, that's the whole point. Capacitive end loading. Did you know that? Capacitive add? Oh, you're just messing with me. Good. And here's the radiation pattern. You see how it all points out in one direction? Most of the energy. That's why they're phase verticals.
It's like a 2 element Yagi.
And then, remember I was telling you that I show you how you can match antennas? So, I think I'm going to break your machine. I told you what the measurement was when I showed the picture of the antenna analyzer, the 18 ohms and then the minus 183 ohms or whatever it was. So, oh, here it is. It's plugged in here. It's 17 ohms and it's 10 ohm reactance. And so I put in this matching network. This program automatically tells me what these values should be. And on the chart, you see where it starts. You put this network in, it brings it to the perfect 1.1 to 1.0 to 1. SWR is reads 1.0. That's the matching section calculated. And when I tied the two antennas together in this bell box, you can see the two antennas on the left-hand side. They're just shorted together. And then there's a little coil of wire and a couple of capacitors. That matches, that gets me to 50 ohms again, right? Because both antennas was fed at 50 ohms. And then here's the SWR curve for these two verticals. And 0.1 is 7.124 megahertz. The SWR is 1.04 to 1. Wow. Pretty close. And the 2 to 1 SWR is from 7.079 megahertz, so 7.08 to 7.17. It stays within 2 to 1. Pretty good bandwidth, right? And then I measured how much current was in each element. You know, they're phased. And you want good balance between the two elements so the pattern works right. And if the top curve is one of the elements, the bottom curve is the other element, and these two currents were within 1.5% of each other. That's pretty damn close. And oh, this guy, I didn't talk about this. There is an antenna designer whose name is Tom Schiller, N6BT, and you'll find him down at Pacificon every year as a featured speaker down there. And he put out this book called The Array of Light. He is a brilliant antenna designer, and he can tell you how much lying antenna manufacturer guys do when they try to sell you an antenna. There's a lot of it that goes on. Oh, this is another antenna I built. This one went in my attic. He's got some dimensions for a 20-meter 2-element Yagi. And then there's this thing called linear loading. I mean, there's all kinds of antenna stuff you can make. And so I designed this little linear loaded 20-meter beam, actually what it is.
Like a folded dipole?
No, it's not folded. What I've done here is I just used the twin lead to impact an element length. And, but I loop back on itself so that it's linear loaded. It's not like a folded dipole, it's actually the full length. So in any event, here's a radiation pattern of that antenna in my attic. And here's the SWR curve of that antenna in my attic. I think it's 1.34 to 1. And the 2 to 1, I didn't get all the frequencies in there, but I think I ended up with about, I don't know, 200 megahertz bandwidth out of a 2 to 1 bandwidth.
Phil, for the radiation patterns, are you using the EZNEC, EZNEC?
That's what it was, yeah.
So if anybody, like you guys with the steel roofs and you want to see, the website is eznec.com.
I think Carol modeled her to
Yeah.
She uses NEC4, but they're both antenna modeling. The problem with modeling antennas is you got to have all the proper parameters for the machine to make the calculations. And most of us don't have enough accurate information to get a truly accurate answer. You're close. You'll come close. I'll give you an idea what's going on. This is what I've got for 10, 12, 15, 17, 20. This is an N6BT antenna. It's a vertical dipole mounted on my chimney. Nobody can see it from the street. So I've got 10 through 20, and his designs are 92% efficient. And again, nobody knows I have an antenna. And that's the end of that. Any other questions, comments?
I have a question, Phil. If you have a metal roof and it's not like a large connected continuous sheet of metal, but it's tiles, and they're, you know, they have like electrical insulation properties, meaning they're not really touching electrical or metallically, because you've got layers of coatings and stuff like that, but you've got shingles. What would you have to say about a roof like that? Would that be equivalent to a roof that's one sheet of metal?
No. But I don't know what it is.
Right.
I mean,
But if it's like metal shingles that are coated with things like plastic and paints and stuff, stone or whatever, that's not going to be like a solid metal roof as far as reflections and interference, right?
Probably not.
Probably not.
I mean,
I can tell you, I use a mobile mag mount right now as my 2-meter antenna. It works great.
Oh, cool.
So it's stuck to my roof, and
You need to sand down each plate and connect them together. Do giant
It
work.
does have a purpose.
To the roof?
Yep.
Like magnetically?
Yeah.
Oh, wow.
there's, you know, everybody's going to have their own elegant solution.
Okay.
I'm going to tell you, experiment. And in today's age, with the advent of this NanoVNA thing, stuff, any of these antenna analyzers are full-blown vector network analyzers. Most of them are designed so that you can do this open short load calibration. And the beauty of that is you don't have to be on top of the tower with this instrument to measure your antenna. Calibrate the feed line, take the feed line to the antenna and sit in your shack. It's a lot safer. And then you're able to figure out what's right and what's wrong. Is your antenna too short? Is your antenna too long? Is the feed point tap too short, or is the feed point tap too long? Those measurements all come straight out. You know what's going on. Life is easy. Don't be in the attic like me, cutting antennas in half, trying to figure out why it won't work. Other questions?
One last question for me. If you were wanting to calibrate for coax, is it okay to calibrate the coax while it's still coiled up in its package?
Absolutely.
It's okay?
Yeah, because it's self-shielding.
Right.
Oh, and this is the other thing. Do you realize that a coax is actually 3 conductors?
3.
Because of the dielectric?
No.
Skin effect.
What?
No. You have a center conductor, and then you have a shield. And these two cancel. It's balanced, right? One field cancels the other. But the outside of that shield isn't shielded. And that's why the balun comes into play, because what ends up happening is the antenna is radiating a signal, and some of that signal ends up on the outside of that coax, and that's how you get signals into the shack. That's the reason for common mode chokes. It's the outside of the shield of the coax that is not shielded, and that's why you use that common mode choke. But your antennas typically will work fine without it. If you have the option of using a common mode choke, I would advise you to do that. But your antenna will work quite well without it.
Huh.
Any other questions? Yeah, I got one. I have another question, sorry.
We don't charge for questions.
I don't want to.
Gert would, but I don't.
So, a
Give you my
feedback
2 cents
question.
worth anyway.
So with the feed line, when I put up my J-pole in my attic, it gives instructions to loop the antenna, in circles.
You know what they're doing there?
Is it a choke? And
That's what it's for. That's what it's for. A J-pole, frankly, has a lot of problems. A J-pole antenna has a lot of issues with feed line radiation. And so they advise you to do some kind of activity to curtail that common mode choke. What you built is an RF choke, radio frequency choke. That's what that is. That's what you've done. And the other way you can do it is you get these donuts and you loop the feed line through 3 or 4 times. J-poles are horrible for that.
Do you have to do that for HF as well?
Typically with HF you use the big ferrite core. You don't have to.
Okay.
But the only thing that it impacts is the radiation pattern. Because once that energy is on that feed line, guess what? Now it's radiating too. But if you put a common mode choke around that feed line, then the only radiation part is the actual element. So you don't get all these extra little lobes. It doesn't hurt
At
anything.
the antenna feed point, you got to put the common mode choke.
Yeah, that's the best practice.
Does that keep noise out?
No.
It's just when we're going.
It prevents the feed line from becoming another antenna, the outside of the feed line.
Resonance as well, too, right? Because
Probably not,
No?
because it's absorbed energy.
I see.
Is the Weensy part of all that loss that we were talking about,
What's that?
radiation loss?
So I use ladder line for my antenna. I don't know why, I just do.
It's great stuff.
Where should I calibrate my NanoVNA? At the end of the ladder line somehow, or do I just do it at the beginning of the ladder line?
Well, let's talk about what's going on here. What's the impedance of your ladder line?
I'm using 300 ohm.
300 ohm ladder line. What's the impedance of your antenna?
It's a loop, so 100.
About 100 ohms. I would make my calibration at the end of my ladder line and see what you read. And then if you can, make another reading right at the antenna and see how the two compare. I think you find the match.
Be interesting.
I've never worked with it, so I don't have the experience.
I've had nothing but issues, so I might switch to normal coax.
Well, make the measurements, and then you'll have a reference. All this stuff is about hands-on. Remember my initial comments? It's the social activity based upon a technical hobby. Deal with the technical.
Yeah.
Where the answers come from.
Have fun learning.
What else? Was it worthwhile?
Yes.
Indeed.
I lied pretty good.
Pretty good.
Well, we know how to cheat.
Cheating is essential.
Let me make a few announcements, if you don't mind. Or you could make, well, we have our breakfast on Saturday.
We have our breakfast on Saturday.
So at Brookfield's at Madison and 80 at 8:30, we have our monthly breakfast. And then on Saturday, same day, this Saturday, so that's Saturday morning, we got you for breakfast. Saturday afternoon at 3 p.m. on 40 meters, you can test whatever you just built or set up on our 40 meter net, 7181 at 3 p.m. 7181. And I'll be around. Are you going to be around? Awesome. Okay. Me or Wilson or Jen KI1TTY usually host that 3 p.m. net. And then of interest, a week from tomorrow, Jen and some of us have been working with the Sacramento Girl Scouts to talk to an astronaut on the space station. And that's going to happen Thursday the 22nd at 10:26 a.m. And we're hoping to live stream that on YouTube and other things. So if we can set that up.
Is that March?
No, February
22.
22.
Okay, you got it.
Yeah, a week from tomorrow. So that's an example of VHF and UHF frequencies not being reflected off the E layer. Right? They go straight up, straight back down. In fact, Bill was doing some satellite work on Winter Field Day.
Fascinating.
Yeah.
Fascinating. I did a lot of satellite.
Bill, was there anything else that, you guys all know about the 10-meter net Wednesday nights right after the 2-meter net? So that is a great opportunity for you guys to experiment. Keyshore, can you do Saturday? Will we be able to hear you on the 40 meters?
I was there last Saturday.
You were?
Hooked it up. I just took my wire,
Yeah.
just strung it on the pole. It was when I
And it works.
And I got on the 40 meter net. And I got that to the measurements if anybody wants to know.
So how'd you get them? Did you, from your radio? Or?
No, from my radio. I
Oh,
also
good.
had a RigExpert.
Nice.
So
Bill, Gert, can you think of anything else to?
Not offhand.
One other thing that's not HF related is Wednesday nights at 9. So we have the 2-meter net at 8, the 10-meter net at 8:30, and at 9 p.m., which is getting a little late, we do the slow scan TV net where we transmit images over our UHF radio.
And it's also streamed on
That's
YouTube.
live streamed on YouTube. That's fun if you guys
Yeah.
want to do something neat to the hobby.
Something to do with the balcony,
Yeah, you can do it. Sometimes you get somebody doing it with a handheld and acoustic coupling, and yeah, it's kind of fun. So you can be on the air with us, or you can watch live on YouTube. What else, Wilson? What other thing? So the next one of these seminars, I think, is March 12th.
It is.
And it's going to be here.
It is March 12th, 6 to 9.
It's going to be here, and Carol's talking about transceivers. Is that right?
I think it says set up your first HF station.
Okay, that's, yeah.
Either way, a month from now, we get to do it all again with a new speaker, so.
Nice work, Phil.
Yes. Thank you very much. Indeed, thank you very much.
We're going to have to look into doing this NanoVNA thing.